Tuesday, paper 2 day, never too soon to start review day. And this question reads, the drag force F sub d acting on a sphere moving through a fluid is given by the expression right there. And it says where K is a constant, rho is the density of the fluid, and V is the speed of the sphere. Determine the SI base units of K. Remember that base units, foundational idea, there are 7 base units to measure 7 sort of base quantities. Quantities are related with an equation. All we really care about for this calculation is the units. And so we can start by saying, I'm going to adopt a convention of putting units in parentheses here. So I've got newtons, which is the unit of force. So that's the left side of the equation. We consider sort of, well, the right side of the equation also has to be newtons of force. K is the unknown. So it's like we're determining the units of K. K has whatever units it must have in order for everything else to cancel out to give us sort of newtons on the left side. Rho is density, they tell us that. And so let's remind ourselves that density is mass per volume, those quantities. And so the units that we measure mass in, kilograms, and the units, the SI units of volume is going to be meters cubed, right? Length times width times height, all measured in meters to give us meters cubed per volume. So for density, we've got kilogram per cubic meter. And then velocity, you may recall, is measured in meters per second, but we have velocity squared. And so we're going to have meters squared per second squared for the units of velocity squared. Right away on the right side of this equation, we see that meters squared are going to cancel out 2 of those. And so we get meter in the denominator and second squared in the denominator, kilogram in the numerator. And then what are the units of K is the question. On the left side, we need to do some expanding here. So F equals ma, that's the equation. Newton's second law is one way to think about Newton's second law, sort of a special case of Newton's second law. And so we got newtons of force again, and this sort of sets the base units, kilograms of mass times meters per second squared of acceleration. So a newton is a kilogram meter per second squared. Substitute that on the left side of the equation. We have a kilogram meter per second squared, which is a newton. And on the right, we can kind of see that that looks a little bit better. It you know, sort of resembles it more. So we already have the kilograms there, good. We already have the second squared in the denominator. The problem is that we've got a meter here, but what we really need is a meter in the numerator. And so K has what units here? It might have some units in the numerator and denominator, but really all we need to do is cancel out that M and make sure that there's one left over in the numerator there. Right, so just by sort of plugging in everything that we know here, K must have units meters squared. So the same units as area. Okay, so maybe it is, it's the area, and that would make sense, right? Like the area of the sphere, how much area is crashing through the fluid would affect sort of the drag force there. Question goes on to state, and you can read it very clearly there, I'll just let you read through that. A ball of weight 1.5 newtons falls vertically from rest in air. The drag force F sub d acting on the ball is given in the expression in A. It says the ball reaches a constant terminal speed of 33 meters per second. Assume that the upthrust acting on the ball is negligible and that the density of the air is uniform. For the instant when the ball is traveling at a speed of 25 meters per second, determine, it looks like we're going to have to determine the drag force on the ball and the acceleration of the ball. Okay. So as I was considering this question earlier, you know, it's like, okay, they give you the expression, we should just be able to plug in everything here. So remember, the drag force is equal to that constant K times the density times the velocity squared. And quickly you realize that they say that the density of the air is uniform, but they don't say what its value is. They also never give the value of K, that constant of proportionality. And so this isn't actually a path to the solution to allow you to determine the drag force using this equation. Rather, we have to sort of be clever and think about, well, what else do we know about this situation? We know the weight of the ball, and for an object to move at constant speed means the acceleration is 0. So if we think about, that Newton's second law that I had up there a moment ago, if the net force equals mass times acceleration and the object is not accelerating, in other words, the right side of this equation is 0, that means all the forces acting on it must be balanced. The up's got to equal the downs in this case because it's a vertical, right? It's falling vertically from rest. So the weight of the ball makes it fall initially, but by the time it's at this terminal speed, there's another force that's equal to weight, right? Namely the drag force. So we know what the drag force is at this speed. It's equal to the weight. We don't know what the drag force is a moment before it reaches that top speed, right? It's asking, hey, when it's only going 25 meters per second, it's yet to reach top speed. What's the drag force at that moment? So we can set this up as a proportion, right? As a ratio. We'd say, well, the drag force that we're interested in compared to the drag force that we know. And really it's sort of the ratio of the drag forces is equal to the ratio of like the right side of the equation. But the nice thing about uniform density and the fact that K is K for constant, those things are going to cancel out, okay? So we really just have the ratio of the velocities corresponding to the drag force, the ratio of the velocity squared rather, is equal to the ratio of the drag forces. And we can use that to solve for our unknown. That is a very useful strategy to have at your disposal for not just solving this question, but lots of other questions. Okay, so keep in mind that idea of a ratio. So the drag force, 1 to drag force 2, I'll just use a 1 and 2 to distinguish them. That's going to be the velocity, at that time, the velocity at that time. So if we make this the thing that we're solving for, the drag force at, when it's going 25 meters per second, we know that the drag force was equal to the weight when it's going top speed 33 meters per second. So we turn sort of the equation that's impossible to solve, because we don't know the density, we don't know the constant, and we can just compare things that we do know. So using a ratio is a very helpful strategy there. This is perfectly solvable. And then this morning when I was sort of working through this, I calculated the ratio of the velocity squared, and then I forgot to multiply it by the 1.5. So it's like, I just took this ratio and recorded that as the drag force. Like, no, multiply both sides by 1.5, right? Solve for it. So it's kind of embarrassing there, times 1.5. But I did it just as a way to emphasize to students, it's easy to make a mistake like a transfer error. You lose track of a number there. It's a shame to know all the physics and set up your proportion correctly just to miss like a 1.5 sort of at the end there. All right, so the drag force is the drag force is 0.86 newtons when it's traveling at a speed of 25 meters per second. As I continue recording this calculation for the benefit of posterity here, we're considering now the acceleration of the ball. 0.86 newtons, you may recall, was the thing that we just calculated here for the drag force. And so now we need the acceleration of the ball. Let's sort of draw a little figure here to help us. We know that the ball has weight 1.5 newtons, and the drag force at the moment that we're sort of interested in is 0.86 newtons, right? So that's how much of it is acting up. F equals ma, we can use this to solve for the acceleration. We have to sort of first calculate what is the net force. It's not like when it's going 33 meters per second and the force is just 0, right? There still is a force, right? Like this is a non-zero force when we go to calculate that. So you can think about it like the sum of the forces, reminding you that there's a vector addition sort of problem here, or the resultant force, is equal to ma. The resultant is, the sum of all the forces. And so when vectors oppose each other like this, we just say, well, one is negative relative to the other one. In order to keep that side positive, I'll say, well, down is the positive direction. So the 1.5 newtons of weight acting down, opposing it is the 0.86 newtons of drag force. So the sum of the forces is just that difference. The mass we'd have to calculate. You may recall that weight equals mass times the acceleration due to gravity. We were given the weight in newtons of the ball. So we can calculate the mass by assuming that we're here on Earth, where the acceleration due to gravity is 9.81 newtons per kilogram, or 9.81 meters per second squared. So if we divide each side by 9.81, we can solve that the mass of the ball is 0.15 kilograms, right? That's just sort of dividing 1.5 by 9.81. So mass equals 0.15 kilograms. And now we've got all the ingredients to solve for acceleration. So I got that 0.86 in my calculator still. I'm gonna make it negative and then add 1.5 to it to get the difference. And so the left side, I realize that there's a sum of forces, or a resultant force of 0.64 newtons equals 0.15 kilograms times acceleration, dividing each side by 0.15 kilograms. I can solve the acceleration as 4.3 meters per second squared. If we take a moment to sort of just think through this problem, or the physics that's at work here, we know that we went from a velocity, our velocity changed from 0 to 33 meters per second, okay? Our acceleration, when we were going a speed of 0, that's right when the ball started falling, right, from rest, right? So the acceleration there, the drag force hasn't had a chance to act on it yet, right? It's not moving through the air to crash into any air to give it a drag force. And so it accelerates just under the influence of gravity. We know that by the time it's going 33 meters per second in velocity, its acceleration has dropped all the way down to 0, because this drag force is becoming more and more pronounced until it's eventually equal to the 1.5, right? As soon as it's equal to 1.5, that's terminal velocity, right? We're no longer going to be accelerating. We've reached our constant terminal, speed, top speed there. And so we just calculated, as we said, well, there's to go from 0 to 33 at some point in that, motion, you were going a speed of 25, right? And when you were going a speed of 25, the acceleration had dropped from 9.81 all the way down to this value, 4.3, right? We solved for the acceleration right at that moment in time, so it makes sense, like that this would be a number that's between 9.81 and 0. And so you always want to kind of consider, the reasonableness of your answers, not when you're sitting for paper 2, when you don't have the time to do it, but as we're studying for it, it's good to sort of, think through all the physics there and make sure that it's all making sense. We could also say, well, what was happening to the force there, the drag force? The drag force started at 0, right? So that's why it accelerated only under the influence of gravity. In other words, but when this thing first started falling, all it had was weight 1.5 newtons down. There was no drag force yet because there was no motion. We know that the drag force, the moment that it was going 25 meters per second with an acceleration of 4.3 meters per second squared, the drag force had picked up to 0.86 newtons, right? That's what we calculated here. And we did that by considering, a ratio, because we knew that when the acceleration is 0, the drag force was going to equal the weight down. So the drag force goes, from 0 to 1.5 newtons, and it's 0.86, sort of, somewhere between there. And so all those things sort of correspond. I think this question has additional parts to it. At least one more part. It says, describe the acceleration of the ball in V as its speed changes from 0 to 33 meters per second. I feel like that's what we just kind of did, or I feel like we did better than that. We talked about not just the acceleration, but the force, the drag force, and how the velocity was changing, as it says here, from 0 to 33. Make sure you're only focusing on the question that's asked. So if it says describe the acceleration, you don't need to talk about how the drag force is changing. It's just the acceleration. So you'd want to say something how it starts out at 9.81, it's the acceleration due to gravity, but then as we accelerate and pick up speed, as that physics sort of suggested, the drag force is proportional to velocity. So as we accelerate and pick up speed, we pick up drag force, according to this, until eventually it's just going to be equal to weight. And that's when the acceleration goes to 0. Okay. So you're basically just saying, you put in your own words, it's going from 9.81 down to 0 as the velocity goes from 0 to 33, just as we mentioned a moment ago. This is Dr. Schleif, still living the physics life. See you next time.